Hello everyone, welcome to Power Electronics lecture number 3. Today we are going to discuss about half wave controlled rectifier. Last time we have introduced about the SCR and today we are going to use that SCR and connect it in a half wave rectifier circuit. Now let's draw the circuit diagram first. So it consists of an SCR. Now we have seen the SCR symbol. It has anode, cathode and a gate terminal. Then we'll connect the AC supply and a resistive load. My output is measured across the load V out plus minus V out. Let me call this as RL and let me call this SCR as T1. Input is V in, which we can write it in the form of Vm sin omega t. Normally this is my single phase 230 volt RMS with 50 Hz frequency. Alright. So if this is 230 volts RMS, what is my peak value of my AC signal? So if this is my AC signal, okay, I have drawn it over here also. So what is my peak value over here? We need to find out. This is my V in versus time. So basically we know the relation that your Vm is RMS times root 2. So it will be 230 root 2. Your peak value of the input will be 230 root 2. Similarly, your we will have minus 230 root 2 plus 230 root 2 minus 230 root 2. All right. So this is my SCR. My SCR voltage across the SCR can be determined as VT1. So basically T1 is my SCR, silicon control rectifier. And we also need to mark the gate current IG. This is my gate current IG flowing into the gate terminal. Alright. And what is my main current flowing through the circuit? So the main current flowing through the circuit will be IRL or ISCR, we can also write, that is VT1. Alright. Now, yeah, so let us start with the working of the circuit. Now we know there are two conditions for SCR to turn on. Alright, so what are those conditions? Let's write it down. So to turn on the SCR, what are the two conditions? First of all, SCR should be in the forward blocking mode. So SCR should be in the forward blocking mode. So what's the meaning of it? That means the voltage across anode and cathode must be positive, and that is happening in the positive half cycle. So SCR is in the forward blocking mode in the positive half cycle of the input. Second, gate trigger IG must be applied at the gate terminal. Alright, so gate trigger pulse, here you can see this pulse should be applied at the gate terminal of the SCR. So when these two conditions are satisfied, then the SCR turns on. And when the SCR turns on, when the SCR is on, it will be replaced with a short circuit. And when the SCR is off, it will be replaced with a open circuit. Alright, so yeah, let's proceed forward. Also there are one more things, little bit of information which I want to give you all is that the IRL is same as the current flowing through the SCR, which is I of T1, which is same as the input current. Alright, now if we apply a KVL over here, if I apply a KVL over here at this loop, so when we apply KVL, we can say V in is equal to VT1 or voltage across the SCR plus V out. Alright, clear it is? V in is equal to VT1 plus V out. Alright, or we can write V in minus VT1 minus V out equal to 0. Alright, that accounts to the same equation. And also, it should be made very clear at the start that VT1 is same as voltage across the SCR. Okay. Alright, we can interchangeably use these things. Okay, so now we have to plot the various waveforms for this. So what are the various waveforms we'll be plotting? We'll be plotting V in of t, then we'll be plotting gate current IG versus time, Then we'll plotting V out, then IRL, and the voltage across the SCR, which can be written as VT1 also. So we can explain the working of the circuit. Half wave controlled rectifier. At the end, we'll say why it is called as a controlled rectifier with the help of these waveforms. Alright, so let's start with the working. Okay, so I have drawn the waveforms over here on the right hand side. Here is my input sinusoidal waveform. Here also let me keep this ready. Okay, so what is Vm over here? Vm is 230 root 2. Alright, let me just expand this waveforms and show it to you. So we have applied the gate trigger pulse. In case of a normal power diode, we don't have this control feature. Basically, the power diode turns on whenever we apply a positive half cycle of the input. The input is positive in the positive half cycle. Alright. So in that case, the diode remains on during the entire positive half cycle of the input. But in this case, we control when do we start, turning on the SCR. So SCR will turn on. There are two conditions to be satisfied, right? SCR should be in the forward blocking mode. SCR is in the forward blocking mode during the entire positive half cycle. All right. So let us start writing over here. So we can say from first cycle is from t equal to 0 to alpha. Okay, so from 0 to alpha, what do we see? Alpha is the instant at which the gate trigger pulse is applied. Alright, so from 0 to alpha, what is the status? So from 0 to alpha, input is positive. My SCR is in the forward blocking mode. Okay, so we can write from 0 to alpha, SCR is in forward blocking mode. That means SCR is off and no gate trigger is applied. Okay, and here we have no IG applied. Okay, before 0 to alpha. So how does the circuit look like? The circuit will look as follows. So let me redraw it. So here we have input SCR. When it is off, it is replaced by open circuit, and here we have resistor, load resistor RL. Alright, and this is my V in. So in this circuit, will the current ever flow? No. The current will be 0. So IRL will be approximately equal to 0. What about the output voltage? Since the current flowing through the SCR is not present, that is 0, the voltage also will be 0. Alright. What about the voltage across the SCR? The voltage across the SCR will be, since we know V in according to KVL, V in is equal to V SCR plus V out. Now over here V out is 0. So what can we say here in this situation? Your voltage across the SCR, we can say, let me rewrite over here with a different color. So voltage across the SCR will be equal to V in. Alright. So let's plot this in the waveforms. So here we have input. Alright. Now let us see where it will start over here. It's starting from, let's say, this is 0 to pi, right? So this is like 0, and here we have 90 degree. This is pi by 2. So somewhere around here we will have, let's say, 45 degree, let's say. So this is the angle, right, which we are talking about, alpha. Alright, and this from 0 to alpha we have to plot V out. So V out is basically 0. So let me mark 0 over here. Let me increase slightly the thickness. So from 0 to alpha, output is 0. What about IRL? Now basically IRL is 0 over here. And what about the voltage across the SCR? The voltage across the SCR is also 0. No, not 0. The voltage across the SCR will follow the input. So from 0 to alpha, it will follow the input like this. This is dotted line is my input, so it will follow the input. Alright, from 0 to alpha. Now let's see what happens when alpha, we have applied the trigger pulse. And when do we apply the trigger pulse? The trigger pulse is applied at t equal to alpha. Alright, So let's go to the second part over here. So from whenever we can write it as this x-axis is omega t. Okay, so we can write when omega t is varied between alpha to pi. Let's say from alpha to pi. So here we need to apply the trigger pulse only once. Alright. There is no need to apply any trigger pulse in the when the input is in the reverse bias or in the negative half cycle. Why? Because in a negative half cycle the SCR is in the reverse blocking mode. So even if you apply a trigger pulse, it won't turn on. So trigger pulse must only be applied during the positive half cycle. Alright. So here you can see there is a second trigger pulse over here. So this is 2 pi plus alpha. This is 0 to alpha, alpha to pi, pi to 2 pi, 2 pi to 2 pi plus alpha, and then 3 pi. Alright. So yeah. So from let's see what happens between when omega t varies between 0 to alpha to pi. So now since the both the conditions are satisfied that SCR is in the forward blocking mode and the gate trigger pulse is applied, we can say that SCR is in forward conduction mode. Okay, so SCR is in the forward conduction mode means what? It is SCR is on. SCR turns on over here. So when SCR turns on, it will behave as a short circuit. It is replaced by a short circuit because the voltage across the SCR is considered to be almost zero. So let me draw the circuit again. This is my V in, and here we have V out. This is my RL. So will the current start flowing in the circuit? Yes, definitely. IRL will flow. Alright. And what is the voltage across the SCR? We'll see now shortly. Since it is a short circuit, it will be approximately equal to 0. What about the voltage across the output? The output voltage is equal to V in. As there is a short circuit over here, V in is equal to VSCR plus V out. And in this case, VSCR is approximately equal to 0. So V out will be equal to V in. Alright. And here we can say IRL flows. Okay, and this IRL is basically will be basically equal to V out upon RL. Okay, so that will be equal to V out upon RL. So it will be of the same nature of V out and will be same nature of V in, but divided by RL value. All right. So yeah, so that's what happens. These are the sequence of events which happens. So let's do it further in the graph. So let's talk about from alpha to pi. So from the period alpha to pi, we have V out, which is following the input V in. So from alpha to pi, we have to follow. It will follow the input waveform. This dotted line is my input waveform. All right, from alpha to pi. And then what about the current? The current nature IRL also will be same, but here the peak value will be Vm upon R. So it will be of the same nature but divided by R. V out Vm upon R. What about the current across, voltage across the SCR? The voltage across the SCR in this case will be 0 from alpha to pi. So this is alpha, this is pi. So from alpha to pi, the voltage across the SCR will be 0. Alright. Now let's see the next cycle. Next, the input goes in the negative half cycle from pi to 2 pi. Alright. And we have seen before, whenever the input goes in a negative half cycle, your SCR will never ever turn on because it is in the reverse blocking mode. So it's very easy information for us. So we can write over here omega t going from pi to 2 pi. So in this case, V in is enters into negative half cycle. Okay, so when in V in is negative half cycle, the SCR will be in the reverse blocking mode. Reverse blocking mode. When SCR is in the reverse blocking mode, Even if you apply a gate trigger pulse, it won't turn on. So SCR will be off. And we have seen before, when the SCR is off, it will behave as a open circuit. This is Vn, the voltage across the SCR, VSCR, and here the output voltage V out. Now, since this is an open circuit, the IRL will be 0 and output voltage also will be 0. What about the voltage across the SCR? Since V out is 0, V in will be equal to VSCR. So the SCR voltage across the SCR will follow the input in this period. Alright, and IRL will be 0. So this happens during the entire negative half cycle. Alright, so during the entire negative half cycle, the SCR turns off. So let me mark this information over here. From pi to 2 pi, from pi to 2 pi, the output voltage is 0. So here it is. The output voltage is 0 over here. Alright. Then what about the current? The current also is 0. And what about the voltage across the SCR? The voltage across the SCR will follow the input. Now input is negative, so voltage across the SCR will also follow it. Alright. So this is what happens from pi to 2 pi. Now let's see what happens from 2 pi to 2 pi plus alpha. Alright, until the next trigger pulse is applied. So let's just see now in the next case. This is the fourth one. When omega t is varying from omega t is going from 2 pi to 2 pi plus alpha. Alright, so trigger pulse happens at 2 pi plus alpha. So from 2 pi to 2 pi plus alpha, my SCR is no doubt in the forward blocking mode. So the first condition is satisfied. SCR is in the forward blocking mode. So that means SCR is off still, because no gate or pulse is applied. So no IG applied still. So when this happens, the SCR turns off, and the same condition will happen as we have seen before. So when the SCR is off, the circuit, the output will be equal to 0. Alright, voltage across the SCR will be equal to V in, as I have shown over here in the diagram, and the current through the circuit will also be 0. So let us quickly reflect that in the diagram. From 2 pi to 2 pi plus alpha, the following thing happens. The output voltage over here, I am plotting the output voltage from 2 pi to 2 pi plus alpha. So output voltage is 0. The current is also 0. What about the voltage? The voltage across the SCR will follow the input till this thing is 2 pi plus alpha. So this is what happens till 2 pi plus alpha. So now in the next scenario, a trigger pulse has appeared. Alright, so we have applied the trigger pulse over here. So at omega t, equal to 2 pi plus alpha, your gate trigger is applied. So gate trigger IG is applied. Alright, so what happens at omega t equal to 2 pi plus alpha? Since the SCR is in the forward blocking mode and we have applied the gate trigger, the SCR turns on. At omega t equal to 2 pi plus alpha, the SCR turns on. And it will remain on during the entire positive half cycle of the input. That means when omega t is varying between 2 pi plus alpha to 3 pi, over here the input is in the positive half cycle, and the gate trigger is applied. Alright, as soon as the gate trigger is applied, the SCR will remain on during the entire duration of from 2 pi plus alpha to 3 pi. So that hence we can write over here, from omega t going from 2 pi plus alpha to 3 pi, what all things happens, the gate trigger is applied and your SCR will now be in the forward conducting mode. So when the SCR is in the forward conducting mode, SCR turns on. Alright, and when SCR turns on, let us quickly draw the equivalent circuit. The SCR, the voltage across the SCR will be 0. SCR is replaced by a almost like a short circuit. So over here, this is my V in, this is my voltage across the SCR, and current IRL flows again. So current IRL flows. What about the voltage across the SCR? Since it is replaced by a short circuit, the voltage across the SCR will be 0, and now my output voltage will be approximately equal to input voltage. All right. So this is what happens when from 2 pi plus alpha to 3 pi. So let us draw that over here. So from 2 pi plus alpha to 3 pi, my output will follow the input. So output is following the input over here like this. All right. Then what about the IRL? IRL also will follow the V out nature, but that will be divided by RL. So your output current, load current will also follow the similar nature to V out. What about the voltage across the SCR? The voltage across the SCR will become 0 for this duration. All right. So this is the status of the circuit from 2 pi plus alpha to 3 pi. And then from 3 pi to 4 pi again, the SCR will remain in the reverse blocking mode, and the following the same sequence of events will happen and the cycle will continue. Okay, so henceforth further the cycle will repeat itself. Further cycle repeats. Okay, so in totality over here, for the half wave rectifier, let me show the circuit. For this half wave rectifier, my as per my gate trigger pulse arrival, my output, I mean the SCR turns on, and then I get the output voltage, and that will follow the input. All right. So this control was not there in case of a power diode. In SCR, we have the control. We have under our control when do we apply alpha and when do we apply next pulse of alpha, that is at 2 pi plus alpha. So this alpha is under our control. We can apply it over here. We can apply it over here. We can even start it beyond 90 degree. But it should be between 0 to alpha, 0 to pi. So the restriction over here is that the alpha should be applied between 0 to pi only. So what is alpha called as? Alpha is called as the triggering angle. Okay, alpha is called as the triggering angle. The SCR will trigger whenever we apply a gate trigger. So at alpha, your gate trigger pulse is applied. All right. So yeah, let's go back over here. Okay. So here we have a control. When do we start, turning on the SCR? And once the SCR turns on, then we'll get the output voltage. And in a negative half cycle, the output voltage is 0, and then the cycle repeat from the next positive half cycle. All right. So that is why we call it as a half wave controlled rectifier. So because we control the conduction period of the SCR. All right. That's why the name. So this is my output waveform or the load waveform. Okay. As you can see over here. This is my IRL, the current load current waveform. It's similar to your load voltage, but it will be divided by RL. Then this is my voltage across the SCR. All right. Now, if you see carefully, the voltage across the SCR over here, the voltage across the SCR waveform and the V out waveform. If I combine them, that will be equal to V in, and that is what is the nature, right? This happens because of KVL. Okay, so V in will be equal to VSCR plus V out. If you combine these waveforms V out and VSCR, you will get back your V in. So alpha is also called as the firing angle. That's more important. Alpha is called as the firing angle or triggering angle or delay angle. All right. So let's revise what happens over here. So from 0 to alpha, SCR is in the forward blocking state. So SCR is off over here. From alpha to pi, let me add over here. From alpha to pi, we have applied the trigger pulse to SCR turns on. Alright. From pi to 2 pi, SCR is off. It is in the reverse blocking mode. It is in the reverse blocking mode. So when once the SCR is in the reverse blocking state or mode, even after application of trigger pulse, it will not turn on. Okay, from 2 pi to 2 pi plus alpha, your trigger pulse is not applied, but still the input is, even though the input is in the positive half cycle, and with no trigger pulse, the SCR will be off because it is in a forward blocking state. From 2 pi plus alpha to 3 pi, my SCR turns on, starts conducting again. Alright. So at omega t equal to alpha, at omega t equal to 2 pi plus alpha, my SCR is triggered on. Alright. So we can write over here at omega t equal to alpha and omega t equal to 2 pi plus alpha, we can say the SCR T1 is triggered on with the application of gate pulse. So that is very, very important. Alright. So these are the nature of waveforms. The load voltage, this is my output or load voltage. IRL is my output current, or we can call it as a load current. And this VSCR is voltage across the SCR. Voltage across the SCR. Alright. And IG is my gate current or a gate trigger. And this is my input voltage Vin. Now let's investigate further and analyze from the output waveform. If I want to find an average value of this waveform, all right, let's say V out average, or we want to find V out RMS. So what all expressions we will get, we'll find out soon. All right. So these are the waveforms. If they ask you in the exam, explain half wave control rectifier, we have to draw all the waveforms, that is input voltage waveform, gate trigger, output load, output or load voltage, output or load current, then the voltage across the SCR. Okay, and we have summarized this number of conditions in various states. We have divided this into small intervals from 0 to alpha. This starts from 0, 0 to alpha, alpha to pi, pi to 2 pi, then 2 pi to 2 pi plus alpha, and 2 pi plus alpha to 3 pi. So explain in your own words why the SCR is off and in which state it is, and how will the triggering angle influence the output. Alright, and why it is called as a control rectifier. I hope by now you have understood why it is called as a control rectifier, because we control the conduction of the SCR when the input is positive in the positive half cycle. So that's why it's called as a controlled rectifier. Alright, so let's go back to this PDF and we have to derive the following now. Let's draw the output voltage waveform quickly. So yeah, let me draw the input in dotted line. It's just a sinusoidal signal. Okay, let me use this. So this is my input. This is omega t. And I have to draw the output. Now we have seen the waveform, how it looks like, right? So at alpha, here we can say at 2 pi plus alpha. Alright. So the waveform is something like this. In the negative half cycle, it will remain off. So it will remain off. And then again, in the positive half cycle at 2 pi plus alpha, it will follow the input. Okay, so this is what the nature of the waveform is. Sorry for the unsymmetry, but it's a symmetric waveform. Okay, so this red color is my output. All right, now this is pi, this is 2 pi. All right, and this is 3 pi. Now let me know what is my period of the waveform. Now first of all, before that we have to find the value of V out average, then V out RMS, and the power factor. Okay, so these three quantities we have to find out. So first of all, you have to define the period. So period is something which repeats itself, right? And the waveform will repeat itself after 2 pi. So from 0 to 2 pi is my period of the signal. So t equal to 2 pi is my period. Okay, and one more thing to notice is that from these waveforms we can see that from 0 to alpha, from omega t going from 0 to alpha, what is my output state? Output state is 0. And from pi to 2 pi also my output is 0. So that is a noticeable thing which will be useful in getting the equations for these three, that is average value, RMS value, and the power factor. So let's begin our discussion with finding the average value of the waveform. So let's solve for V out average. Alright. So what's the average value waveform expression given by? V out average is given by 1 upon t integral 0 to t 0 to t V out of omega t d omega t. Alright. Now in this case, let me start the derivation. So V out average will be equal to 1 upon t, t is 2 pi. So 1 upon 2 pi, 0 to 2 pi. Um, V out omega t is actually equal to V in omega t, and that is V in omega t is what? Vm sin omega t. Alright. So in this case, we can write over here from 0 to 2 pi, we have Vm sin omega t d omega t. But in some cases my V out is 0 also, right? So let us split this interval into three parts. 1 upon 2 pi, 0 to alpha. Alright. So from 0 to alpha, my output is 0. So this is 0 omega t. Then alpha to pi. We can see from alpha to pi we have Vm sin omega t d omega t. And from pi to 2 pi, we again have 0 d omega t. Alright. So in summary, we have to find between alpha to pi. So V out average will be given by, we can take Vm out because it's a constant, Vm upon 2 pi alpha to pi sin omega t d omega t. Now integral of sin omega t is minus cos omega t. So we can write Vm upon 2 pi minus cos omega t, where omega t is going from alpha to pi. Alright, so let's write it further. So V out average will be given by Vm by 2 pi. So minus of pi, cos pi, and then minus you will get omega t. Instead of omega t, we'll write cos alpha. So minus of minus cos alpha. Now we know cos pi is minus 1. You can check it out in your calculator. Cos pi is minus 1. So this will be equal to Vm by 2 pi. This is minus 1, this will become plus 1, and this will become plus cos alpha. So that is my expression of the output. V out is equal to V average is equal to Vm by 2 pi 1 plus cos alpha. Alright, so this is my expression for the average value of the waveform for a half wave controlled rectifier with R load, with a resistive load. Alright, so this is my average value of the output or load voltage. Now this V out average can also be written as VDC. Just remember, it will come in handy when we solve the numerical. It can also be written as VDC because it's a DC component of the signal also. Alright, so this also proves that the output depends upon the firing angle alpha. Okay, so here we can say that V out, average value of V out depends on alpha, which is the firing angle. So your alpha is my controlling parameter. Your alpha is controllable. Okay, we can decide where we'll apply alpha. So whenever we substitute alpha equal to, let's say, 0, alpha is 0. Whenever alpha is 0, it becomes a normal, whenever alpha becomes 0, my V out average will be, this will become 1 plus 1, that will become Vm by pi. And in that case, my output waveform will be like this. So we have no control over here at all. Now that we apply alpha, not equal to 0, that is, it can be between, so alpha can be between 0 to 90 degree or 0 to pi by 2, we can say, in radians. Alright, so we can decide where we apply alpha. So alpha can be over here, alpha can be over here. Okay, so alpha is under our control, that's why it's called as a hence it's called as a controlled rectifier. So it's proven from the V out average expression also. Now let's find the expression for V out RMS. So second is V out RMS, and that formula is given by 1 upon T integral 0 to T. We write V out RMS square, so that will be V in square d omega T dt. Okay, so that's the formula of V out RMS square. Over here T is 2 pi, your V in is Vm sin omega T, and your d, instead of dt we will write d omega T. Okay, so this is sin omega T. Alright, let us substitute the values. Actually this is V out only. V out square omega T, and here in this case we say that whenever SCR is on, your V out will be equal to V in. Alright, and we said, we also seen that this is valid between the interval alpha to pi only, because from 0 to alpha output is 0, and from 2 pi to 2 from pi to 2 pi your output is 0. Okay, so under these two conditions we need not write the integral. So directly we can write V out RMS square is given by 1 upon 2 pi 0 to 2 pi Vm sin omega t the whole square d omega t. Alright, and we know from 0 to alpha and pi to 2 pi my output V out is equal to 0. Alright, so we can write V out RMS square will be equal to 1 upon 2 pi integral 0 to pi Vm square sin square omega t d omega t. So let's solve this further. Now we know sin square omega t can be written as 1 minus cos 2 omega t by 2. Okay, so we'll substitute over here and let's continue further. That is V out RMS square will be equal to, now we can take this Vm square out, so we can write Vm square by 2. Okay, this pi also we can add. Vm square by 2 pi will be equal to, here instead of sin square omega t we can write 1 minus cos 2 omega t by 2. Alright, so let's solve it further. D omega t, that is V out square RMS will be equal to Vm square by, let's take this 2 also out, so Vm square by 4 pi, and here integral of 1 will be omega t minus integral of cos omega t will be sin omega t, so that will be sin 2 omega t divided by 2. Okay, so this is the integral, and limits will be omega t going from alpha to pi. Okay, so let's solve this further. That is V out square RMS will be equal to Vm square upon 4 pi. So here we have to substitute the values. So here you will get omega t, it is pi minus alpha. Okay, pi minus alpha, and here you will get sine of, instead of omega t substitute pi, so 2 pi, okay, minus sine 2 alpha divided by 2. So that is what we get. Okay, and sine 2 pi is 0. We know sine 2 pi is 0. The value of sine 2 pi is 0. Okay, so after substituting further, we can calculate V out RMS square will be equal to Vm square upon 4 pi. Here we get pi minus alpha. This will become plus sine 2 alpha divided by 2. Alright, so that is what we get, and we can take this pi inside. So what do we get? V out RMS square will be equal to Vm square upon 4 divided by, into 1 minus alpha upon pi plus sine 2 alpha upon 2 pi. Alright, now this is V out RMS square. We can, most of the time we can use this formula directly, no problem at all, but it's better to write V out RMS. So V out RMS will be, this Vm by 2 will come as it is, and then this will be 1 minus alpha upon pi plus sine 2 alpha upon 2 pi, the whole raised to half. So that is what we get, the final form of V out RMS. So this is my RMS value of output or load voltage. So very quickly we have got the output voltage expression. Of course the unit will be in volts. Here remember, alpha is in radians. When this alone, when it is not associated with sine and cos, alpha is in radians. Alright, and pi also will be in radians. It is 3.14. Okay, so if I have, let's say, if for example, in case of, you might be knowing the conversion between angle to radians, right? So let's say we have 90 degrees. How do we convert it into radians? Multiplied by pi by 180. So that will become pi by 2 radians. Let's take one more example. Let's take 45 degree. So when we have 45 degree multiplied by pi by 180, so what do we get? Pi by 4 radians. I hope it is clear by now. Alright, so this is what we need to do for finding the expression of RMS value of the output voltage. Now let's find out the power factor. That's the last thing to do for this lecture. Power factor. So power factor, short form, we can write it as PF. It is defined as average power divided by apparent input power. Apparent input power. So that will be given by P out divided by V in RMS into I in RMS. Alright, and what is P out RMS given by? P out value is given by, P out value is V out square RMS divided by RL. And here in our case, we know that I in will be equal to I out RMS. We have seen that, right? The current remains same, and that is given by V out RMS upon RL, since we have a resistive load. So let's substitute these values over here. Therefore, we can say power factor will be average value P out is V out square RMS divided by RL, and that is divided by, here we can write, instead of V in instead of I in RMS, we can write here V in RMS into V out RMS upon RL. So let's see what gets cancelled. RN and RL gets cancelled. Here we get V out, and here this V out gets cancelled. So finally, what is the formula for the power factor? The formula for the power factor will be V out RMS divided by V in RMS. Okay. So that's the formula for a power factor for a half wave control rectifier using resistive load. All right. Yeah. So for the half wave full wave for a half wave fully controlled rectifier, we have found out the expression for the power factor, RMS value of the output load voltage, and the average value. Now let's do one more thing. Let's just simulate this in LT Spice, the circuit. I've kept the circuit ready in LT Spice. Okay, we have taken the model of the SCR and I have applied through the circuit. Yeah, so this is what the expected waveforms I should get at the output, right? So let's just describe this. So we have applied the input RMS value of the input V in will be around 60. Okay, supply frequency is 50, and we have taken an SCR. We have applied the gate trigger, and RL value is 5 ohms. So let's just simulate this circuit. Yeah, so this is what do we get. This is my input, this is my gate voltage, the gate current, sorry. This is my voltage across the SCR, and this is my current across the load RL. Now I'll share a detailed link of a separate video which is explaining SCR half wave control rectifier with R load, how to do all this in simulation in LT Spice. So watch out for that. Now let's just compare this waveform with the waveform which we have drawn. It's quite similar, it's resembling. Okay, so this is my, if I want to take a separate, let's say plane plot for plotting V out, yeah, that's it. So this is what we have drawn. Input voltage is sinusoidal voltage, Vm is around 60, and your V out waveform is something like this. Here we have seen, right? Yeah, this is my nature of the waveform. As you can see, it's similar. Then I have my IRL. IRL nature is same. Only thing is here the unit is different. Here we have Vm upon RL. All right, and we can see evidently Vm is 60 over here. RL is 5 ohms, right? So 60 upon 5, that will be 12 amperes. All right, so we are getting that perfectly. And then the voltage across the SCR. You see the voltage across the SCR waveform is exactly the similar, the way we have drawn over here. All right, and this is my gate current waveform which we apply only during the positive half cycle. Here we have shown 3 cycles, here we have shown 2 cycles while explaining. Alright, so waveforms are technically correct. Now let's find out the the values of it, average value, whether it's correct or no. So the average value of the waveform will be given by Vm upon 2 pi 1 plus cos alpha. Alright, so first of all, how to find the average value over here of this waveform in LT Spice? Just move the cursor around it, just press Ctrl and click on it. So that will give me the average value. Average value of this waveform is 16 volt, RMS is 28.134. So let me write it over here somewhere. So by simulation, what are we getting the average value? Your V out average is coming out to be 16 volt, and V out RMS, okay, just a second. Let me save this file first because it's on since a long time. So it's a little bit unresponsive at the moment. So this is how we can calculate the average and RMS value from the waveform. We are just cross checking what we have done. Okay, so this is RMS equal to 28.134. So let's cross check with the formulas which we have derived. Okay, so let me take this aside. Let me take this formula over here. Okay, let me close this. Let me measure the peak value. Now we have considered an actual diode, so let me measure the peak value. The peak value over here, if I measure, it is around 59.02. Okay, so VM value is 59.02. All right, so VM is 59.02. Now let's calculate the value. This is what we got from the waveform. All right, so let's apply the waveform. Let's apply the formula over here. V out is Vm by 2 pi 1 plus cos alpha. So V out is Vm by 2 pi 1 plus cos alpha. So we substitute V out equal to Vm is 59.02 divided by 2 pi into 1 plus cos alpha. Now how do we find alpha? Alright. Now over here, let's take the cursor over here. Let me take the cursor over here. This is around 10 millisecond. Okay, so this is corresponding to pi. Now let's go and check how much is this value. Let me expand this part. So this value is around 2.5 millisecond. Okay, so the timing corresponding to alpha is around 2.5 millisecond. So let me do some calculation over here and show it to you. So here we have in the waveforms part, this is what we have. We are finding the value of alpha. So for 0 to 10 millisecond, and your alpha starts at around how much value? 2.5. So the ratio is around. It's applied at 1/4 value. All right, and normally we have a period 0 to pi. So 1/4 of this will be pi by 4. All right. So my alpha will be pi by 4, and pi by 4 is nothing but 45 degrees. All right. So pi by 4 is around. How do we get 45 degrees? Pi by 4, we multiply it by 180 by pi. So this pi and pi gets cancelled. This is 290 and this becomes 45 degrees. That's how we got alpha as 45 degrees. So here we can substitute cos of alpha, that is 1 plus cos 45 degree. And if you plug in the values, that will be close to around 16 volt. You can cross check the answer. All right. Similarly, we can VRMS is 28.134. Let me cross check it. So I'll remove it. I'll take the cursor over here, press Control and then press on this. Yeah, 28.134 of the output waveform. Now let me cross check with the formula. Okay, this is the formula. So we have to be careful in this case. Let us substitute the values over here. So V out RMS, VM is 59.02 divided by 2 into 1 minus alpha has to be written as pi by 4. It is pi by 4, right? So pi by 4 upon pi minus plus alpha should be written in radians like this. Sine of alpha is 45 degrees. So here we write it in the form of degrees, 90 divided by 2 pi raised to half. So this becomes 59.02. Here we'll get 1 minus 1 by 4 and sine 90 is 1. So 1 plus 1 divided by 2 pi raised to half. So if you solve this, you will get an answer close enough to 28.134. So you will get an answer close enough to 28.1. Alright, so you can cross check this answer in your calculator, you'll get closer to 28.1. Okay, so this is how we verify the waveforms. We verified that the formula derived are correct, V out RMS, and similarly we can find the power factor also. So in this case, your power factor formula is V out RMS upon V in RMS. All right. So V in RMS also we can find out. So we can place it over here, cursor over here, press Control and press on this. So RMS value, I mean average value of the AC input waveform will be definitely 0. RMS value will be 42.43. So V in RMS is 42 point. Let's just check it out. Okay, let me place the cursor over here. 42.43. This is V in RMS. And how does the V out RMS came for us? For us, the V out RMS was around 28.134. Okay, so let me add it over here. 28.134. So power factor will be 28.134 divided by 42.43. So this is how we can calculate. You can write this number. It will be lesser than around 0.5. And yeah, this is how we can calculate the power factor also from the waveforms. All right. So yeah, we have come to the end of this session. We have seen the working of a half wave controlled rectifier using with R load. We have drawn its waveform one by one for all the cases, and we have also verified the waveform in LT Spice, and we have also derived the expression for the power factor, output load voltage, average value of the load voltage, and RMS value of the load voltage. Yeah. So yeah, that's it for this session. Next time we'll start with a full wave control rectifier with R load. So thank you all for joining.